Okay, if you guys would turn your attention to this video, I think that this does a really good job of showing exactly what we want. I'll make it large, and I'll pause it from time to time as well. But the second derivative shows us something called concavity. And we'll see what it says, okay? So we have two pieces. We have concave up, and we have concave down. And then she'll show a graphical method here as well as a table method of how we could see that. She has technology that could show this that I don't. Okay, hold on to kind of set up here. If this is a graph and this is the point of tangency right here, this red dot, and that black line right there is the tangent line, you tell me, is the slope positive or negative? So is the function increasing or decreasing? All the way until we get to this point, right? Okay. Now, this table value right here says the slope is 1. This is going to change. What she's going to do is she's going to be able to move this point to different parts of the graph, and you're going to see the slope change. Now, I'll tell you ahead of time, okay? This portion of the graph right here, do you think that this is concave up or concave down? Concave down. And then this section of the graph right here is concave up. And the point right here where concavity changes is called the inflection point. That's where our second derivative is equal to 0. Now, I could show you guys all that algebraically. What you need to try to understand is watch as she moves this. This slope is 1 right now. Tell me, as she moves this line, is the slope going to increase and get bigger or decrease and get smaller? It's going to decrease. So as the slope decreases, that's what makes it concave down. Once the slope is like this and we continue to move it, will the slope increase or decrease? It will start to get closer to being positive, okay? So watch as she tries to show that, and you can see it, okay? Here you go. Negative 0.9, negative 1, boom. And then it moves from negative 1 back to negative 0.9. See how it switches? It got to negative 0.99, then to negative 1, and now it's starting to go back up. Okay, as you look at, they broke that up into tables. You see right away it started at 1, and it was decreasing. It went down to 9.94. So because the value of the slope is decreasing, it's concave down. 0.7, 0.5, 0.2, negative 0.1, negative 0.4, negative 0.7, negative 0.9, negative 0.99. After it gets to negative 0.99, it starts to go up. Negative 0.86, negative 0.64, negative 0.35. Starts to go up. So therefore, it's concave up after that spot. Okay, this is the confusing part that people don't always get. Is the first derivative positive or negative here? Positive. The second derivative tells us if the first derivative is increasing or decreasing. Is the first derivative increasing or decreasing? It's getting smaller. The first derivative will be getting smaller in value. So although the first derivative is positive, the second derivative is negative, which makes it concave down. Slopes are decreasing, slopes are decreasing. Now they're finally increasing. Let's not review it anymore. Let's go straight to our worksheet, which I gave you. Let's try a couple of problems. Make sure that you have out your graphing calculator as well. So it says, for the following functions, identify local max and mins, as well as inflection points, as well as intervals of concavity. At the top, please write this down, okay? F double prime of x equals 0 tells us inflection points. An inflection point is the point where concavity changes. Concavity changes. Also write this down. F double prime is positive. It's concave up. F double prime equals negative. It's concave down. Now, I could give you the book definitions. We might move to that at some point, but right now I just want you to understand the bare minimum. Okay? Now, just because f double prime of x is equal to 0 doesn't necessarily mean that we have to have an inflection point. We don't have to have an inflection point, but that's generally where they exist. So let's look at the first one. Okay, it says for the following functions, identify these pieces. And we'll look at graphically, we'll tie it all together for you. And I have a couple problems on the backside for you to try. F of x equals 1 over 3 x to the third minus 4x plus 2. First thing I want to try to start to identify is where I might have local max and local mins. What is the derivative of this function? X squared minus 4. So in order to find possible local max and local mins, I set that derivative equal to 0. And I get 0 equals x squared minus 4, so x is equal to. So it's very possible that I have local mins and maxes that exist at positive 2 and negative 2. Very possible. We'll check graphically here in a little bit. F double prime is going to be important for me to check concavity as well as inflection points. What is F double prime of x? I'm going to set that equal to 0. 2x equals 0, so x is equal to 0. Now, I showed you how to do interval testing just the other day for f prime of x. Tell me this, when we were testing to see where f prime of x was positive, that told us where the function was increasing. And where f prime of x was negative, that's where the function was decreasing. Now I'm going to check f double prime of x. Okay? If f of x is equal to, or the inflection point happens at x equals 0, then my concavity probably will change there. We will check. Here's one interval from negative infinity to 0, and from 0 to positive infinity. We are going to check to see the value of f double prime of x in those intervals. Right. And my factor, or my f double prime of x, the only factor that exists is 2x. So what's a number that you could plug in between 0 and negative infinity? Negative 1. 2 times negative 1 is, it's negative. So f double prime of x is negative over that interval. I plug in, say, positive 1, and I get a positive value. So it is probably positive there. So that means that if f double prime of x is negative, is it concave up or concave down? Concave down. And how about where it's positive? Concave up. That's what we would that we know is true. Okay, we know it's concave down and concave up there. All right. Now, if it's concave down, is that going to be a max or a min? A max. So the maximum probably occurs in this interval where it's concave down, and the minimum probably occurs where it's concave up. Let's take out our graphing calculators and see visually what's happening here. Y equals 1 over 3 x to the third minus 4x plus 2. Look at what we found. Okay, without actually graphing it, we've identified that at x equals 0, right here is the inflection point. That's where it occurs. That's where the concavity changes. Everything to the left of that point is concave down. Everything to the right of that point is concave up. And so we've identified that inflection point. We could see the points of concavity. We could see that at -2, yes, it has a local max. We could see that +2, yes, it has a local min. So this has been pretty valuable information for us to say something interesting about the function. Now, I told you guys on Friday how to find intervals at increasing and decreasing. Now we're switching that up just a little bit, okay? If we went over a certain interval, then they would be. But because our interval would be defined from -infinity to +infinity, we won't define our absolute max and mins at this point. But our local mins and our local maxes, did the local min happen at 2 or -2? 2. What is the function evaluated at +2? I'll check it out. I'll plug in a value of 2, and I get -3 1/3. So at the point 2, I have a local min, and it has a value of -3 and 1/3. Now, I want you guys to know, again, I know it was a local min because local mins have that shape wherever it's concave up. At point 2 is the interval where it's concave up. It's concave up at +2. Local max is going to occur at f of -2. And at that point, if I plug in -2, I get 7 1/3. That's where it's has my local max. What's my inflection point? 0, and I'm going to put the y value as well. 0, 1, correct? Whoop, 2. The interval for where it's concave up is going to be from 0 to +infinity, and concave down is going to be from -infinity to 0. Question? Nope. This one right here? Please write this down above here. I didn't make note of this. I think that this will help you, okay? F prime of x is equal to x squared minus 4, and write down f double prime of x equals 2x. Just right above there, I just wrote the derivatives. Just to remind us one time, if I plug any number in for f prime of x, any number, what will it tell me about the function? Okay, and it will also tell me the increasing or decreasing. And if I plug a number, let's say I plug in the number 5. I get 2 times 5 is 10. What does that tell me about the function? 10 is positive, so that means that it is concave up. So I could ask you, hey, is the function concave up or concave down at x equals 1? And you would plug 1 into here, and you'd say 2 times 1 is 2. That's positive, so it must be concave up at that point. I could say, well, is the function increasing or decreasing at 1? Well, you would plug it in here. 1 squared is 1, minus 4 is negative 3, so it must be decreasing. So at the point 1, it's decreasing, but it's concave up. Those are important features that we need to know about the function. Today is just kind of a bare bones lesson, though. We'll apply more of this later. I want to do the same thing here, okay? I want to identify all those intervals. We have negative x to the fourth plus 2x squared. We'll be able to go to work here. F prime of x is? Very good. F prime of x is negative 4x to the third plus 4x. So I set this equal to 0. 0 equals negative 4x to the third plus 4x. Factor out a negative 4x times x squared minus 1. So I get 0 equals negative 4x times x plus 1 times x minus 1. Okay, so it looks like I have critical points that exist at 0, negative 1, and positive 1. Most likely, since it's a nice polynomial, I'll have, I very well might have some local maxes and mins there, but we don't know for sure. We just know something interesting happens at those spots. Okay? F double prime of x is equal to 0. What is F double prime of x? Maybe 12x squared plus 4. So if I solve for that, I get 0 equals negative 12x squared plus 4. 12x squared equals positive 4 divided by 12. X squared equals 1/3. So x is equal to plus or minus the square root of 1 over 3. What did I just find? Where the concavity changes, your second derivative set equal to 0 tells you your point of inflection. That's where concavity changes. So it looks like we have 2 points where concavity very well might change. Okay? X equals plus or minus square root of 1/3. Let's figure out the square root of 1/3 real quick so we can get a decimal here that we can work with. Square root of 1 divided by 3, 0.577. Okay, so I have some intervals where the concavity may be changing. The first interval is going to be from negative infinity to negative 0.577. What's my second interval? Yep. And what's my third interval? Okay. And we have our second derivative, which is this negative 12x squared plus 4. I didn't factor it into pieces. It doesn't have to be factored. That sometimes just makes it easier to actually test. We could put that there. Let's test the value of this thing over these given intervals. What number between negative infinity and negative 0.577 would you like to plug in? Negative 1. So negative 1 squared is 1 times negative 12 is negative 12 plus 4 is negative 8. So is the second derivative positive or negative over this interval? It's negative. So that means that it is concave down. What number would you like to plug in here? 0. And you get positive. So that means it's concave up. And this last point, if you plug in a positive 1, you get a negative result, which means it's concave down. So it does look like we have inflection points that do exist. We have inflection points that do exist, and concavity does change. Okay? Concavity does change. Let's look at this graphically. Negative x to the fourth plus 2x squared. I'm going to zoom in on that a little bit. I'm going to change my window to be negative 4, positive 4, negative 2, positive 2. And when I look at that graphically, we could see the nice change. You tell me when my marker hits what you believe to be a point of inflection. Again, point of inflection is where concavity changes. You tell me when you think I'm at an inflection point. Yep. Good. Very good, everybody. Okay. You tell me when you think I get to the next one then. So how many do we have? Yeah. And you can see it's at negative 0.577, positive 0.577, but that's where your concavity changes. Now, can you see local mins and maxes? How many of those do we have? We have 3, okay? So let's identify these points now and finish this off. Intervals where it's concave down. Intervals where it's concave down is going to be negative infinity to negative 0.577 and positive 0.577 to positive infinity. Intervals where it's concave up is simply from negative 0.577 to positive 0.577. What are my inflection points? Yep, so we'll plug those into my function. We'll see what we get for results. We plug in negative 0.577. We get 0.55. All right. So that's an approximation. It looks like it's going to be same for both of them. The only reason I know it's true for both of them is because the graph is completely symmetrical, is it not? So the local max, local mins. I have 0, negative 1, and 1. Local min at 0. F of 0 is 0. Local max at f of 1 and f of negative 1. Now will give us what? 1. There you go. Ashley, Claire, got to go? Oh. All right. Well, later, guys. You guys, I'm ready to have you start on the back side, just those 4 problems. But let me finish off by saying one thing, okay? As you guys can go, that's fine. This isn't super important. But you tell me this. I have a local, or I know something interesting happened at 0. Okay? Something interesting happened at 0. It's either a local max or local min. You tell me. Local max, is it concave up or concave down? Down. So if I plug in, say, 0 into my second derivative, If I plug in 0, do I get positive or negative value? Positive. So at 0, it must be concave up. So it must be a min. Whereas if you plug in 1 or negative 1, if you plug in 1 or negative 1, you're going to get negative values. And therefore, it must be concave down. So you don't even have to check graphically to see whether or not you have local mins or maxes. You can use your second derivative test to truly find out. So I know it gets tricky handling a first derivative and a second derivative, but you got to kind of keep it straight. Think first derivative is increasing, decreasing, local mins and max. Second derivative is inflection points and concavity, and that will help you out. So if it'll help you out at all, we really don't do third derivatives, okay? So there you go. Get to work on the back side, start applying this learning. You guys should be good to go.